Our universe exhibits some strange qualities, and matter approaching absolute zero temperatures can attest to that. Examining the properties of matter under these conditions could lead to some awesome implications in supercomputers, even levitation. So let's get into the strange world of ultra-cold matter. To understand the awesome behaviors of matter at absolute zero, let's first explain what that is. Absolute zero is 0 degrees Kelvin or negative 273 degrees Celsius. This is when molecular motion stops and molecules and atoms are at their lowest energy levels. Wonder why the energy isn't zero? This is because of zero-point energy, which prevents the energy from ever being zero in order to abide by the Heisenberg uncertainty principle, which will be discussed later on. Right now, particles in the air are zipping around at about 1,200 miles per hour, and this number will get slower the lower the temperature is. At extremely low temperatures, quantum mechanics takes over and things start to get spooky. As a group of particles approach absolute zero, they can be described with a certain wave function, and that increases the colder it gets. These wave functions overlap and interact with each other so that they can be seen as one coherent wave, known as a Bose-Einstein condensate. This effect of phase coherence can allow for superfluidity and superconductivity to occur. Now, if this is confusing to you, don't worry, because they're really quite easy to understand. Superfluidity is when a fluid can move without friction. They can seep through tiny holes that no other liquid can and do not lose any kinetic energy, even if swirled around into a vortex. They even appear to defy gravity and flow up and over the containers that hold them. Superconductivity is almost the same as superfluidity, but with charged particles. It's when a current can flow without any resistance at all. It will never stop and it will never heat up. This is incredibly useful for supercomputers because an extremely large current can be maintained using superconductivity, and not to mention the lightning-fast speeds. Ouch! Now, all this talk must sound great, and you might think, why hasn't more research been done? The problem with reaching absolute zero temperatures is that it's impossible as we know it. Just as traveling at the speed of light, removing an endless amount of heat requires an endless amount of work to do so. Also, the Heisenberg uncertainty principle doesn't allow for particles to reach absolute zero, and thus, zero-point energy takes place. As the particles stop, the momentum becomes zero, a known value, which means that we must know nothing about its position. It might not even be in your observations. It could be anywhere at all. You're joking. Now don't be discouraged because experiments have already come super close. Scientists at MIT managed to cool sodium atoms down to 0.45 nanokelvin. That's about 566 billion times colder than your freezer. Perhaps reaching these ultra-cold temperatures can actually help us to understand how these particles behave. What better way is there to observe these particles than by trying to get them as still as possible? There is much more research to be done on this spooky phenomenon that occurs near absolute zero temperatures, and the possibilities of applications are endless.